Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment&Health. Eco-Environment&Health is a journal initiated by prestigious scientists with a strong editorial board including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design and broadcasting. The experts will accompany you like an harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Hi, Alex.
Hello, Professor Wang.
Long time no see. How are you?
Yeah, good. Here with Chunchi, you know, all is good. Research going, and yeah, you?
Not bad.
That's good.
It's afternoon in Norway time, right?
Yeah, it's 3 p.m. 3 p.m. now. Yes.
Okay.
So shall I share my screen or how we will do it?
Just wait a moment. Yeah.
Okay.
Okay, let's begin. Good evening and good afternoon, ladies and gentlemen. This is Lei Wang. It is a great pleasure for me to welcome you to the talk at EEH. Thank you to each and every one of you for being here with us today We are very happy that the distinguished scholars from different countries can share your knowledge and experience through EEH. And today, Dr. Junjie Zhang at Norwegian University of Science and Technology will host the question and answer session. Junjie, can you say hello to us? Yeah, and I believe that today's talk will be an interesting and stimulating experience to you all. Today, the speaker is Alexandra Asmakupluza. Alex is my good friend, and we met in Virtual Center in New York. Most of the audience today are Chinese, especially some people will watch it on the video platform. So please allow me to introduce Alex in Chinese. And I reveal the little secret that Alex also learned Chinese for a period of time.埃里克桑德罗博士，他是挪威科技大学化学系的副教授，他在希腊的雅典国立卡波济斯特里安大学获得分析化学的硕士学位和分析化学的博士学位。他是美国化学会会员，也是 CTEC 的会员。那么 Alexandro 博士呢，他在分析化学 EST 还有这个 Environment&International 等知名的学术刊物上发表了80多篇论文，并且也获得了广泛的引用。他的研究呢，包括开发基于液相、气相和质谱以及串联质谱的有机污染物的衡量分析方法和技术，并且呢，用以评估人类暴露以及识别和开发暴露的这种污染物的这个生物标志物。那么今天他带来的题目呢是污染物和暴露生物标志物的生物监测和环境监测进展。Okay, Alex, it's your turn. Welcome.
Yeah. So thank you, Professor Wang. Share this window, presentation. Yep. Share. So now you should be seeing the presentation, correct?
Yes.
Okay. So thank you, Professor Wang, for this nice introduction. Actually, we know each other, I think now 10 years. And throughout the past 10 years, I had the privilege to work with top research scholars and professors from China. So having said that, thank you for the invitation for today's talk. My talk today is titled Advances in Biomonitoring and Environmental Monitoring of Contaminants and Biomarkers of Exposure. We will have a closer look to the analytical tools in order to achieve efficient and fast analysis in the field and the context of environmental chemistry. So currently, I serve as an associate professor at the Department of Chemistry at NTNU, the Norwegian University of Science and Technology. So what did we do in terms of research the past year? And because a picture is worth 1,000 words, I present in the left side here a picture, an infographic that was generated from Scopus with keywords of what was our research all about the past year. So you can see we have worked on perfluorinated chemicals, plasticizers, and we have analyzed them with different techniques, including liquid chromatography that we will go into more depth later on. And we have done that. We have measured different chemicals and biomarkers of exposure in different contexts. We have performed analysis in the context of circular economy, or for marine mammals research, or for plastics. Even human biomonitoring and other types of biomonitoring like raptor biomonitoring. But in all these projects and types of analysis that we have been involved, what chromatographic technique did we use? So when it comes a research problem challenge in our lab, and we need to perform an analysis on a specific topic, we always think if our analysis and our chemicals are not volatile, then we choose one of these three analytical techniques for our problem. Either we will use HPLC, high pressure liquid chromatography, or ultra performance liquid chromatography, or another type of chromatography that is not so popular, the supercritical fluid chromatography, or else a synonym, if you would like a word, convergence chromatography. And we try to take the best of all worlds, if you would like, so that we can achieve a rapid analysis. Why we prefer rapid analysis is because in our lab, the cost per sample goes with the duration of the analytical run. In addition, in environmental chemistry studies, a lot of research associates want to analyze multiple samples in a limited time frame so that they can export as much data as possible for the outcome of the research project. So we aim, and I can say the strength of our laboratory here at NTNU is to perform fast analysis in order to accommodate and our research challenges, but in the fastest and the most economical way. So the content of the presentation actually involves three main topics. First, we will explore the benefits of ultra-performance liquid chromatography versus the classic liquid chromatography in the context of phthalate metabolites analysis, which are metabolites of a particular class of pollutants called phthalates. Then we will move on with plasticizers and personal care products like bisphenols and benzophenone UV filters. And we will close this topic with describing the method performance characteristics of our organophosphate flame retardants methodology. Then in the section 2, we will go deeper into convergence chromatography, and I will try to promote this type of chromatography because it's still underexplored, while it can provide many benefits for us, the environmental chemists. And we will see special case studies when it comes to novel brominated flame retardants, but also steroid hormone analysis. Then in the final section of our presentation, we will use all the advantages of UPC square and UPLC and tailor them to a single rapid sample preparation protocol in order to maximize our output in terms of analysis and in terms of using as little sample as possible and exporting, maximizing the data that we can export from it. So first things first, UPLC analysis of phthalates metabolites. So to put it into perspective, phthalates metabolites are the metabolites of our plasticizers or else softeners called phthalates. And they're actually found in considerable concentrations in the environment. They have been detected in humans, they have been detected in marine mammals and other species. So in the left side here, you can see the parrot phthalate, the original, if you would like, chemical that is found in many plastic products. And on a little bit right side, we have the corresponding phthalate metabolite. Like, for instance, the methyl phthalate has the phthalate metabolite of monomethyl phthalate, and here it's its abbreviation. You can see the structure of these metabolites. Generally, they are single-chain ester compounds, where here the ester chain has different lengths and different structures. So a lot of projects require the analysis of these chemicals because they are widespread. So on the left side here, we have a typical chromatogram from a human urine sample where we used an HPLC system, and our core column was the ultra aqua C18 column. Please note that a lot of these metabolites are very polar. For instance, phthalic acid is a very small and polar compound. The same goes for a methyl phthalate metabolite. But phthalic acid is really polar. And generally, this chemical is preferred to be analyzed with helic or normal phase chromatographic approaches. So using this ultra aqua C18 column, we use a column that is actually better and improved for the retention of such chemicals. That's why you can see the chromatographic peak that is very straight and not disturbed. Also, it can separate the isomers that we are very much interested in, and the rest of the chemicals are being retained with a typical C18 column mechanism. So the column here, the size of the particle diameter is 3 micrometers. So in our recent research, when we measured these chemicals in harbor porpoises, we applied UPLC. We applied UPLC because we wanted our analysis to be faster so that we could process and analyze more samples at the same time. And as you can see, our chromatographic run is 11 minutes and is approximately 3 times shorter and 3 times faster than our HPLC system. Of course, the size, the length of the column is different, but also the particle size is considerably smaller than the 3 micrometers column that we had in the HPLC system, 1.3. But this column, unfortunately, exists only in a thoroughbred C18 stationary phase. We don't have different variations of columns like the ultra aqua C18 column where it can accommodate the retention of polar chemicals. It's only exclusively appropriate for a little bit more non-polar chemicals than phthalic acid. And you can see here that our peak actually, even though we perform faster analysis, it is, I can say, disturbed. But in this case, where phthalic acid is the end product, if you would like, of the metabolism of phthalates, generally is found in high concentrations and high abundance in our samples. So even if we obtain a little bit disturbed peak, we still fit our, this column fits our purpose of our analysis. We can measure phthalic acid. Also, baseline separation of the isomers, as you can see here, that are very challenging, had excellent separation and comparable and even superior than the one that we achieved on the left side with the HPLC system. Overall, faster analysis, good separation of the isomers, and acceptable, if you would like, peak shape of our phthalic acid made this method the main method that we applied in the paper that I just mentioned. But what extraction protocol did we use? Generally, we couple most of our methods that we have in the lab with classic SPE, solid phase extraction protocols, or liquid extraction protocols. Of course, I will explain later on another type of solid phase extraction that we use that is very efficient in our case. So these phthalates metabolites were extracted with liquid extraction initially, and then we passed it through solid phase extraction so we could clean up the eluent and then directly take it for a UPLC analysis. This SPE cartridge that we use, ABS Elute Nexus, is very particular because it has big, larger pore size sorbents and makes it easier and better for bioanalysis of different chemicals. That's why we preferred this SPE in our case. And as you can see, the matrix effects, that is basically how much the signal gets suppressed in our case from the matrix, from the liver, we see generally acceptable matrix effects, but for the more polar compounds like phthalic acid, we have a loss of signal even close to 76%. Nevertheless, as I aforementioned, phthalic acid is found in high abundance, and even with matrix effect challenges, we still could continue and perform the analysis. When it comes to identification of our chemicals, we regularly use ion ratios also, so we could certify for sure that this is the target analyte that we are looking for. And here are the typical retention times of our UPLC fast method for phthalates metabolites. Another interesting class of contaminants that we are working here are the plasticizers, bisphenols, and benzophenone UV filters. Due to the similarities in their structure, these two chemical classes are co-determined in one single chromatographic run. Generally, in our lab, we try to find similarities between the chemical structures of different classes. So because that can be interpreted, that can be seen later on when it comes to analysis, that we can incorporate both groups in one single analysis rather than having two or more different methods. So the chromatography that we used, we applied it at least in two papers. Here we have two recent examples. One where we applied it in environmental samples, in actually microplastic fiber samples from synthetic textiles. And we explored environmental degradation of these fibers. And then on the right side, we applied the same actually chromatographic method for the assessment of the bioaccumulation of these chemicals in wild raptor species. And of course, in both cases, we found concentrations of both chemical classes. So the method that we applied is a method of runtime of 4 minutes. In these 4 minutes, on the left side, you can see the chromatographic separation. We achieve chromatographic separation optimal and excellent chromatographic peaks. The only two chemicals that we don't baseline separate are bisphenol M here and bisphenol P. We have the choice to baseline separate them if we would increase the gradient. However, because these chemicals are generally found in very low abundance, in some samples, if any abundance whatsoever, we decided instead of increasing by 1 or 2 minutes our method, it would be better to stick on the 4 minutes so that we can have a higher sample throughput from our system and analyze more samples on the same period of time. The challenges here were generally the unstable retention time of the more polar compounds, bisphenol S and benzophenone 2. But it was actually expected because, as I said in our previous example, this is a C18 thoroughbred column and doesn't have any aquatic, any properties for retaining more polar chemicals. In order to deal with the challenge, we were supplied with C13 internal standard, especially for BPS, so that we could make sure that we don't have any false positives in analysis. Once you get a C13 internal standard specific to your target analyte, then because the C13 and the target analyte are sharing the same physicochemical properties, then there's no problem whatsoever when it comes to positive identification or not of your target analyte in actual samples. Before that, we were using an HPLC system, HPLC column, where we had our chromatographic run in 20 minutes. And of course, in this case, we were able to shorten our analytical time by 5 times. And when we do that, it means that we could provide to the customer or the research project a significant cheaper price per sample. Here I present to you 2 typical examples, case studies for environmental and biological sample. When a sample comes in our lab for analysis and the chemical classes are specified, besides checking literature about protocols available for our case, we generally try to apply generic protocols for extraction. We have seen from experience that simple extraction protocols, well, with using a non-polar solvent like ethyl acetate or dichloromethane, can actually extract the majority of the chemicals that you are analyzing. If you want to take it historically, pharmacopoeia and first pharmaceutical analysis, when they were happening, the chemists were using back then as main extraction solvents ethyl acetate, dichloromethane, or methyl tert butyl ether. These were the 3 main solvent extraction solvents. So we have such generic methods based on these solvents for extracting our samples generally for biological applications, because these solvents can also precipitate the high protein content of our samples. But when it comes to environmental media, we generally prefer solid phase extraction. On the right side, you can see that a typical SPE extraction protocol with either Strata X RP cartridges that are more focused to reverse phase interactions with our target analytes, or we can use strong cation or strong anion or weak cation cartridges. Then we can actually focus more in our classes that we are interested in. And in the case of bisphenols and benzophenone UV filters, we could reach low limits of detection in the nanogram per liter range or the nanogram per kilo range by extracting and pre-concentrating our samples through solid phase extraction. Please note, in biological sample, this is not very openly said, but generally you avoid to pre-concentrate your samples because due to the high endogenous concentrations of other biological chemicals like proteins, phospholipids, and so on. So if you basically pre-concentrate, what will happen? You will pre-concentrate your matrix interference in your analysis. So always we need to think the fit for the purpose of our analysis. So generally, as in this case where we analyzed the multiple chemicals back in 2016 for different chemical classes, we generally approach these problems and these challenges by applying generic protocols where possible. Generic liquid-liquid extraction, solid liquid extraction, or solid phase extraction approaches. And generally, as I mentioned and I highlighted, generic protocols decrease the amount of sample needed and generally are cheaper and more time efficient. And if you can couple these protocols to parallel methods running in UPLC or supercritical fluid chromatography platform, then you can maximize your output. But in all cases, we need to make sure that we don't make things more simple than they should be. In our chemical class of organophosphate flame retardants, we were using in the past a 25 minutes chromatographic method. And this chemical class is known as a novel flame retardant contaminant class. And this is something that in our lab, it's been asked more and more recently to perform analysis for. So we established a fast method with a UPLC system that was 5 times faster than the typical HPLC methods out there. And on the left side, you can see the chromatography. And on the left side, you can see the chromatography. And on the right side, you can see typical retention times and the ion ratios of each of our chemicals. So, but the real problem with OPFRs is the background contamination. It's something that is generally not reported so much in papers, but it can actually be a challenging problem. So a guide for performing successful OPFRs analysis is to use as clean as possible chromatographic columns, do thorough cleaning of all instrumentation that you will use, but also we have installed after the mobile phase eluent, we have installed another C18 column so that we could delay any contaminant leaching from the mobile phase. Because these chemicals are found everywhere, they are widespread. So we tackle this problem by cleaning before and after analysis the system thoroughly and monitoring the background levels, while also regularly changing pre-columns and adjusting, adding the second column after the mobile phase to delay the elution of any contamination that derives from there. Now, going deeper in the UPC square, the convergence chromatography, I know that many of you don't have experience on this, and it's something new in environmental chemistry. But we explore it and we see more and more applications in our everyday analysis in our lab. So here I will present 2 case studies on novel brominated flame retardants and steroid hormone analysis. The second actually paper is currently under review in Talanta. So first chemical class, novel brominated flame retardants. Characteristics, the main characteristic of this chemical group is the diversity. A lot of chemical class, as you can see on the right side, have different, very diverse chemical structures. So we need to find a type of analysis where it can accommodate that. And what I mean by this is like some chemicals prefer more GC, gas chromatography analysis, as a typical flame retardant. But other ones, like tetrabromo bisphenol A or 2.463-bromophenol, prefer HPLC. So convergence chromatography is a compromise for both worlds. So here we started for comparison with a liquid chromatography system that we developed. You see on the left side, we check different columns, like kinetic C18, EEH C18, different in-vial solvents, meaning the solvent that you have in the vial that you send for analysis, different gradients, additives in the mobile phase, flow rates of the mobile phase, and column. And we ended up with a C18 column with this in-vial solvent and a gradient of 24 minutes. In these 24 minutes, we were able to separate the isomers of HBCD, alpha, beta, gamma, And overall, we performed good chromatographic separation. On the downside, we had decreased sensitivity for actually the chemicals that preferred gas chromatography. And that was a challenge. But when it came to liquid chromatography analyzed chemicals like HBCD, our separation and our performance were very good. The only downside of it, it was 24 minutes long, the method, and that's a challenge. So in UPC square or convergence chromatography, we did the same. We checked different chromatographic columns like the UPC square HSS C18 and the UPC square CSH fluorophenyl column. Please keep in mind that in the market, there are only 2 or 3 types of columns available. It's not like HPLC that we have a big variety. But the thing that a lot of people don't know is that you can actually use your columns of HPLC and apply them and use them in a convergence chromatography system. So you just simply take your column, your UPLC column, and apply it in a UPC square system. So here we had the challenge. We tested again in-vial solvent, gradient, and organic phase. Basically in UPC square, the thing that I need to mention is that we have supercritical fluid carbon dioxide where we add organic phase as an additive. So from our experience with UPC square, we saw that actually the most critical, one of the most critical parameters for good chromatographic separation is the in-vial solvent that we take for analysis. That is not, it is a critical parameter, but it's not so crucial as it is in UPC square. Because in UPC square, the challenge that you have is that you need to make and obtain good chromatographic peaks. And in order to do that, you need to optimize in large detail the in-vial solvent composition. So here is our UPC square method, UPC square method. And as you can see, we have baseline separation of our isomers, A, B, C, HBCD. But the peak shapes are the most optimal that can be achieved. When you compare UPC square with UPLC, comparing peak shapes can be a little bit challenging because by default, UPC square you have a hard time to obtain optimal peak shapes. Nevertheless, this method with this 5-minute gradient on an HSS-C18 SB column and heptane isopropanol 9-to-1 as the in-vial solvent was found suitable and optimal for further analysis. So with this method, we were able to go 5 times faster in our analysis and have a little bit higher sensitivity for the GC analyzed compound than we had with LC. Our final class that we analyzed with UPC square are the steroid hormones. And these steroid hormones are 19 analogs with similar, if you would like, structures. And here is a 20-minute UPLC method. And I'm highlighting the derivatives where they were isomers and we needed baseline separation. And here is the method with 5 minutes, achieving even better, actually we're achieving baseline separation. So steroid hormones analysis is nowadays something that we have a lot in our lab. We provide a lot to our research, to other research groups that they need steroid hormones, like in the aquaculture industry or in biological analysis, they need steroid hormones analysis. So we can provide fast and cheap steroid hormones analysis so that they can associate it with contaminants or diseases or other variables that they have in their research context. Finally, all these UPC square and UPLC platforms, if you can tailor them to a single rapid sample preparation protocol, then you can achieve an even higher throughput of samples. Nowadays, you all know that legacy and novel pair and polyfluoroalkyl substances, the so-called PFAS, and the most popular compounds, PFOS and PFOA, are something that a lot of people are analyzing biological samples. In addition, they would like to analyze some biomarkers of exposures. So they want the profile of steroid hormones or the profile of thyroid hormones to see if there is an imbalance in the hormonal system. So we, in our lab, we have a single extraction method, a hybrid SPE method that needs less than 1 minute for completion. Either it's blood, plasma, serum, or urine, less than 1 minute of completion. And then the eluent, we take it in our 5-minute method in the UPC square, 8 minutes for our thyroid hormones, or 4 minutes for our perfluorinated chemicals. Then we are reaching the order of hundreds of samples analyzed weekly. This is the chemical class of perfluorinated chemicals, like PFOS. This is a classical PFC, while Gen X is a typical novel PFAS. And here are the retention times within 4 minutes of all our chemicals. And here you can see the nice chromatographic peaks that we have achieved. Thyroid hormones. We use the UPLC system with an Atlantis 18 column. Again, it's a column where it promotes the retention of polar small chemicals. And in this case, we use C13 internal standard for all our target analytes. And therefore, there's no need for us to do matrix match quantification, meaning you don't need to quantify in actual samples. Rather, you can do it in a simple calibration curve in a solvent solution with the internal standard method. And that provides us a faster analysis of a diverse set of samples. The hybrid SPE that we used has the cartridge, if you want to analyze how it cleans up our samples, is actually having a compartment where it retains phospholipids. Zirconian groups are actually grabbing phospholipids, while there is a filter also here where it retains proteins. So the sample passes through, retains proteins, retains phospholipids, and has your target analytes ready for analysis. Comparing with other methods that we had, we find the least matrix effects experience with this method compares to typical SPE or liquid-liquid extraction. And here our protocol is like basically 100 microliters of blood, serum, plasma. We add 300 microliters of precipitation reagent. Then we pass them through the hybrid SPE, and they are ready for analysis for these 3 chemical classes. Conclusions, observations for rapid analytical approaches for basically answering the questions that are generated from the environmental chemistry front. Generally, UPLC decreases the time of analysis. In our lab, if we cannot achieve an analysis of less than 10 minutes, we try convergence chromatography or supercritical fluid chromatography. We always aim for developing generic protocols unless it is not possible. We evaluate fragmentation pathways of our target analytes, like in the case of steroid hormones, in relevance to the resolution time, so we can avoid any crosstalk issues, false positives, peaks showing up in places that they should not. Generally, we spend some time in improving peak shape in UPC square applications. And finally, we need more stationary phase types with 1.3 micrometer particle size columns. This is the column that we use mostly in our lab. So remember, make things simple, but do not oversimplify. Unfortunately, though, literature shows sometimes, occasionally, the opposite happen. At this point, I want to thank my major funding sources, Sludge Effect, It's a project of circular economy. We do these chemicals, we apply these techniques in a circular economy context. Cost impact is a project where also Dr. Chunchi Zhang is working on, and we apply these analytical tools for the analysis in birds. And RAS Health is an industry-related project related to aquaculture, where we are trying to improve the Atlantic salmon production by having fresh, high-quality water in recirculating aquaculture systems. Thank you all for your attention. And here is more information in our website if anybody wants to explore more. Thank you.
Okay, thank you, Dr. Markopoulos, for your great presentation. Okay,
you are welcome, Dr. Zhang.
Yeah, okay. This is the QA part. Does anyone have any questions? Because I think in the room, you also can raise your hand if you are in the other platform. Maybe you can just to write your questions. Let me check for other platform.
Yeah, and yeah, if you have questions, please ask, or if you have more complicated questions, also you can send me an email or send to,
yes.
To Dr. Zhang.
Okay, I can ask a question for.
Okay.
Alex, I think for our Chinese audience, I think most of us is more interesting for the UPC square, because
yes,
most of us we know these instruments, but we don't know much. Can you tell more about the advantage and or the disadvantage of the UPC square?
Yes. So the UPC square uses is, if you want to imagine it, is something between, if like GC, gas chromatography, and liquid chromatography got together and had a kid, the kid would be supercritical fluid chromatography. Okay. Meaning that it takes the advantages of both worlds. So instead of using a gas phase and instead of using a liquid phase, here you're using a supercritical fluid phase, where you can function the instrument below the supercritical fluid point or above, where what do you achieve by that? You achieve fast mass transfer between the mobile phase, that is the supercritical fluid, and the stationary phase. And faster mass transition means faster analysis, faster peak separation. So in some instances, it looks like GC, where you can have high separation efficiency. But also it analyzes chemicals that don't need to be volatile, like in liquid chromatography. In GC, we need to heat up the samples, and the volatile chemicals are the ones that we analyze. Well, in supercritical fluid chromatography, if you have LC analyzed chemicals, you can actually move your analysis to supercritical fluid. However, many of the mechanistic, though, explanations, what is happening, like the peak shape or other things, are largely today unexplored. So that's why there's room for a lot of applications. And basically, there's room for many types of analysis. As you know, in our lab, many chemicals that we analyze in the LC, we try to check them if it's possible to be analyzed with supercritical fluid chromatography. Advantage, it's faster. Disadvantage yet is not fully developed so that we can have a UPC square columns, a variety of columns available, I think.
Okay, thank you so much. I think it will be helpful for the Chinese audience. Maybe they want to use the UPC square in the future. Yeah.
Yeah, I think so. If in modern analytical and environmental chemistry, someone that wants to go further should explore UPC square. There's a tendency we try to explore untargeted or suspect screening analysis, putting focus on the mass spectrometry aspect of analysis. But we should also put focus on the development in the chromatographic part. So a lab, I think an analytical chemistry lab needs to be evolved and developed also towards that direction.
Yeah, I totally agree with you.
So yeah.
So does anyone want to say something? Okay, I also didn't find any question from other platforms.
Okay.
Okay, maybe I think it's more about analytical things.
Yeah.
Yeah.
So yeah. So and it can be complicated. So yeah. So it's no problem if there's though some now the attendees know about supercritical fluid chromatography and its benefits. So if they have any question, they can
Just contact you or me. Yeah. Yeah.
Yes.
Okay. Okay. Finally, I would like to thank Dr. Asmakopoulos again for the nice presentation, and thank the organization of EEH, and thank everyone for coming today. Have a good day or night. Goodbye.
Bye-bye.